Hey, welcome back to Fat Mama Physics. In this video, we are also going to be looking at uncertainty propagation, but this time we're going to look at what happens if you take a number with uncertainties and you multiply it or divide it, for that matter, by a constant. So this one is actually not in your data booklet, and but it is something that I want to show you, which does come up quite often, and then maybe potentially another way, another perspective you can take in doing your uncertainty propagations, okay? So let's get down to what this means. When you multiply your number by a constant number p, and p is just any number, you will need to multiply your absolute uncertainty by p as well. That's very easy. You multiply by p, then you also have to multiply your absolute uncertainty by p. Same goes for dividing. So then, because the data booklet doesn't have that, we can use this function to explain it, to show what that looks like. So if y is equal to your constant times a value, then the absolute uncertainty of your y is going to be that same constant times your absolute uncertainty of a. Okay, so you might have done a similar example before when you had to say, look at the one oscillation where your data contained all 10 oscillations and you had to divide everything by 10. That was an example of that. So I'm just going to do the one example here. Hopefully it's pretty straightforward. Let's say we want the absolute uncertainty of pi times a. And don't forget, I have just set some values of a, b, and c for us to use when we're doing these examples. So let's calculate what pi times a is equal to. Okay, we multiply, we get 23.4999. And just a constant times meters, so the units stay as meters. And for the absolute uncertainty of our result, we do the same thing. We take pi times the absolute uncertainty of a, which is 0.03 meters, and we get 0.094. And now it's time to write our final answer. So it looks like 0.09. We can do a quick check. This is roughly, oh, hey, look. This one is actually less than 2% relative uncertainty. So we actually have to round this to two significant figures. So I'm going to actually write a note here so we remember. So because of that, I'm going to have to round it off to two significant figures because it is smaller than 2% relative uncertainty compared to our original number. So that's going to be, it was 0.0942, so that's just 0.094, which means our original value here, 23.499, also needs to be rounded off to the thousandths place, and that is 23.4991. Okay, so that 1 doesn't do anything. It doesn't round the 9 up or down. So I keep it as 23.499 meters. And this is plus minus our absolute uncertainty rounded to two significant figures, 0.094 meters. And I will bracket this off. So that's our answer for example 3. Now, this is an interesting thing to think about. And maybe a chance for you to try it out first, but let's read it together. If you took the relative uncertainty of A and multiplied it by the result, so that's pi times A, would that give you the same answer as example 3? If you are not sure, yes or no, show your work to help you explain. Okay, so what that is instead of multiplying your absolute uncertainty of A by the constant, you take the relative uncertainty of A, which then, actually, to be more specific, take the fractional uncertainty of A, and then multiply that by the final answer. See if you get the same thing. Good time to pause the video for you to try. And here, let me show you it now. So fractional uncertainty of A which is this, is going to be 0.03 meters divided by 7.48 meters. And then I'm going to take this and I'm going to multiply by our final answer. So that's pi times A, which is 7.48 meters right now, okay? You might notice it's funny because notice the 7.48 meters, this just cancel out like that. Yay! And then that just leaves you with 0.03 meters times pi, which is exactly how you did it in the previous example. And that should say example 7. No, wait. 1, 2, 3, 4, 5. This should say 5, okay? Oh, my previous example numbers were wrong too. Okay. Anyways, not important. So that's going to give us the same number, 0.094 meters, okay? So it is exactly the same thing. And why do I make you do this? Because it shows you two ways how you can grab the absolute uncertainty when you are doing something or you're manipulating your number with the uncertainty. Let's say you have to manipulate your number in a way that may not just be as simple as multiplying by a constant. It could be anything, like if you're taking some sort of inverse, or if you're doing something fancy with, whatever that is. It just shows that if you're doing these kind of functions, the fractional uncertainty of your number doesn't change. It's the percentage of a whole that stays the same as you're continuously manipulating it. That does not apply when you are combining two data values that have uncertainties themselves. But if you're just propagating this one thing, then that relative uncertainty stays the same throughout. It's just a tactic that you can use. And this is just showing you two ways you can do it if you're, say, multiplying, which is not as difficult, okay? So hopefully this video gave you a bit of tools to help you with propagating uncertainties. I thank you for watching. Good luck. Fat Mama Physics, seeing you next time. Next video, we're going to talk about exponents. Fat Mama Physics, signing out for now.